Hey there, tech enthusiasts. Today we're diving into the fascinating world of computer architecture. Think of it as the blueprint for how your computer works. It's the foundation that dictates how all the components talk to each other. Computer architecture defines the system's functionality from the CPU to the memory and peripherals. It's a bit like designing a city. You have your city center, which is like the CPU, managing everything. Then you have your transportation system, which is like the bus, connecting everything together. And of course you need places to live and work, which is like the memory, storing all the data. Understanding computer architecture is key to understanding how software interacts with hardware. It's the bridge between the ones and zeros, and the amazing things your computer can do.
Now, let's meet the star of the show, the CPU, or Central Processing Unit. This tiny but mighty component is the heart and soul of your computer, tirelessly working behind the scenes to ensure everything runs smoothly. This is the brain of your computer, the command center that executes instructions. Without the CPU, your computer would be nothing more than a collection of inert hardware. It's the CPU that breathes life into your machine, processing data and executing commands at lightning speed. It's like the conductor of an orchestra, making sure everything works in harmony. Just as a conductor ensures each musician plays their part at the right time, the CPU coordinates the activities of all the other components, ensuring they work together seamlessly. The CPU is made up of several key components. Each of these components plays a crucial role in the overall functioning of the CPU, working together to process instructions and manage data. We have the Arithmetic Logic Unit, or ALU, which handles all the math and logic operations. The ALU is like the mathematician of the CPU, performing calculations and making decisions based on logical comparisons. Then there's the Control Unit, or CU, which fetches instructions and tells other components what to do. The CU acts as the manager, directing the flow of data and instructions within the CPU, ensuring that each component knows its role and performs its tasks efficiently. And let's not forget the registers, small, super-fast memory locations that hold the data the CPU is currently working on. These registers are like the CPU's personal assistants, always ready with the information it needs to perform its tasks quickly and efficiently. Think of them as the CPU's personal assistants, always ready with the information it needs. They provide the CPU with quick access to the data it needs to execute instructions, ensuring that the CPU can work at maximum speed. Finally, we have the Instruction Set Architecture, or ISA. The ISA is the language the CPU understands, the set of instructions it can execute. It defines the commands the CPU can perform and how it interacts with the rest of the computer system. This is the language the CPU understands, the set of instructions it can execute. The ISA acts as a bridge between software and hardware, translating high-level programming languages into machine code that the CPU can process. It's like a communication protocol that ensures software and hardware can work together. Without the ISA, the CPU wouldn't be able to understand the instructions given by software, making it impossible for the computer to perform any meaningful tasks. The ISA ensures that the CPU can effectively communicate with software, enabling the computer to perform a wide range of functions, from simple calculations to complex data processing.
Next up, let's talk about memory. Memory is a crucial component of any computer system, acting as the workspace where data is temporarily or permanently stored. This is where your computer stores data, both temporary and long-term. Without memory, your computer wouldn't be able to perform even the simplest tasks. Think of it as your computer's short-term and long-term memory. Just like how you remember things for a few seconds or for years, your computer does the same with different types of memory. We have different types of memory, forming a hierarchy based on speed and cost. Each type of memory serves a unique purpose and is optimized for specific tasks. At the top, we have cache memory, which is super fast but also expensive. Cache memory is built directly into the CPU or located very close to it. The CPU uses this to store frequently accessed data for lightning-fast retrieval. This minimizes the time the CPU spends waiting for data, significantly boosting performance. Then there's the main memory, also known as RAM. RAM stands for Random Access Memory, and it's the main workspace for your computer. It's slower than cache but larger and more affordable. RAM is where your computer stores programs and data that are actively being used, allowing for quick access and smooth multitasking. This is where your computer stores programs and data that are actively being used. The more RAM you have, the more applications you can run simultaneously without slowing down your system. And finally, we have secondary storage, like hard drives and SSDs. These are used for long-term data storage, holding everything from your operating system to your personal files. This is where data is stored permanently, even when the computer is turned off. Hard drives and SSDs come in various capacities, allowing you to store vast amounts of data. It's like the library of your computer, holding all your important files and documents. Whether it's photos, videos, or work documents, secondary storage ensures that your data is safe and accessible whenever you need it.
Section 4. Speedy Gonzalez. Pipelining for performance. Now let's talk about making things faster. One clever trick CPUs use is called pipelining. Imagine an assembly line where each step is handled by a different station. That's essentially what pipelining does for instructions. Instead of waiting for one instruction to be completed before starting the next, the CPU breaks down the process into stages. Each stage is handled by a dedicated part of the CPU, allowing multiple instructions to be processed simultaneously. Think of it as multitasking on a hardware level. This parallel processing significantly speeds up execution, making your computer feel snappier and more responsive. It's like having multiple workers on a construction site, each handling a specific task.
Section 5. Parallel universes, multi-core and beyond. Speaking of parallel processing, let's talk about multi-core processors. These are the heart of modern computing, revolutionizing the way our devices handle tasks. Remember how we said the CPU is like the brain? Just as our brain can handle multiple thoughts and actions at once, a multi-core processor can manage several tasks simultaneously. Well, a multi-core processor is like having multiple brains working together in harmony. Imagine the efficiency and speed when several brains collaborate on a problem. Each core is essentially an independent processing unit, capable of executing instructions on its own. This means that tasks can be divided and conquered more effectively. By dividing the workload among multiple cores, the CPU can handle more tasks simultaneously. This parallelism is what makes modern processors so powerful and efficient. This is especially beneficial for demanding applications like video editing, gaming, and scientific simulations. These tasks require immense processing power and speed, which multi-core processors provide. It's like having a team of chefs in a kitchen, each working on a different dish to prepare a feast faster. Each chef, or core, focuses on a specific task, ensuring everything is done efficiently and quickly. And it doesn't stop there. The advancements in multi-core technology continue to push the boundaries of what's possible in computing. We also have technologies like hyperthreading, which further enhance the capabilities of multi-core processors. Hyperthreading allows a single core to handle multiple threads of execution. This means that even more tasks can be managed at the same time, boosting overall performance. It's like giving each chef the ability to cook multiple dishes at once, further boosting performance. This technology ensures that our devices run smoothly, even under heavy workloads. As we look to the future, the potential for multi-core processors and parallel processing is immense. With ongoing research and development, we can expect even more powerful and efficient processors, capable of handling the most demanding tasks with ease. The future of computing is bright, with multi-core processors leading the way. From everyday tasks to complex simulations, these processors are the backbone of modern technology, driving innovation and progress.
Section 6. Specialized silicon GPUs, FPGAs, and more. Now, not all tasks are created equal. Some require specialized hardware, and that's where specialized processors come in. One prime example is the GPU or graphics processing unit. Originally designed for rendering graphics, GPUs excel at parallel processing, making them ideal for tasks like video editing, gaming, and even machine learning. Think of them as the artists of the computer world, bringing images and videos to life. Then we have FPGAs or field programmable gate arrays. These are highly customizable chips that can be reconfigured after manufacturing. This flexibility makes them suitable for niche applications like signal processing, cryptography, and prototyping. Think of FPGAs as the chameleons of the chip world, adapting to different tasks as needed. They bridge the gap between general-purpose processors and custom-designed circuits.
Section 7, Cloud Atlas, virtualization and its impact. Now let's step outside the realm of individual computers and into the cloud. Cloud computing has revolutionized how we access and utilize computing resources. Virtualization plays a key role in this revolution. It allows us to create multiple virtual machines on a single physical server, each running its own operating system and applications. This enables efficient resource utilization, as multiple users can share the same hardware without interfering with each other. It's like having multiple apartments in a single building, each with its own occupants and amenities. Cloud computing and virtualization have significant implications for computer architecture. They drive the need for scalable, energy-efficient, and secure systems that can handle massive workloads.